Today we're going to start at section 9.4. It's our last section in chapter 9. This section's a little confusing. It's going to talk about some counting strategies. You may have encountered them before. Sometimes they're encountered in an Algebra 2 class. Sometimes you look and you see them inside of like a contemporary class if you're taking contemporary here on campus. It also may be something where, I mean, it's obviously a step above what you would be teaching at a K-12 level, right? Like I could get that for the most part for your certification. But you do tinker in some of these areas, just not to the full extreme, right? That happens in a lot of our sections where we get toward the end and it's just a little bit more, but you should know more than your students. So that's a good thing too. All right, so let's take a look at some permutations and combinations. You may or may not have seen this notation before. Have you seen factorials? The little exclamation point. Okay, good. It does not mean that you're excited. Right? Not math. It doesn't. What it actually means is that you're doing some multiplication. And the multiplication is wherever it starts the first number. So if this says n, you have that number n, and then you go down one and you do n minus 1. And you go down another one and you do n minus 2. And you keep going down until you get to 1. And you multiply them all together. So definitionally, because we're going to need it later, we define 0 factorial to be the number 1. It's not a provable fact. It's a statement that we need to be true to if other things hold. Sometimes it feels like when people do that in math, it's sort of cheating. It's definitely not. If you remember in geometry, there are some undefined terms as well, where you're just like, we just take it to be that this is what we sort of mean. Point and line are some of them. You have a picture in your mind of what those are, but there was never actually like a proof that said this is what a point is. Somebody just said it's kind of like this, right? This is kind of like that too. There is a definition for 0 factorial. It is the number 1. So when we're looking at something like 4 factorial, all we are doing is we're multiplying 4 times 3 times 2 times 1. And when we get to 1, we stop. And then we just multiply them. And feel free to grab a calculator if you'd like. This one's not very big, so you can probably do it in your head if you wish to. What is 4 times 3 times 2 times 1? Yeah, it's 24. Okay, is that all right? Okay, so I'm going to actually introduce something that we've used, but you weren't really told about it necessarily in the last section. It's called the fundamental principle of counting. If you've taken number theory, you've seen it before. If not, it's not a big hairy deal here. It's a very simple process. It simply tells you if there's 2 events that are occurring, then you can actually multiply their results together to figure out what the total number of ways are for that event to happen. Like it's in steps. All right, so if you talked about, like how many shirts you have and how many pants you have, and you ignored fashion, or maybe they just all color coordinated, right? You can figure out how many outfits you could wear because it's a 2-step process when you're putting your clothes on. So there's 2 events, and this works for more than 2, but this is the way it's set up. 2 events, M and N, and if M can be occurred in little m ways, and N can occur in little n ways, we multiply M times N to figure out how many ways it can happen. This was what we were doing when I was talking about my dice just a minute ago, right? You roll the dice, and there's 6 ways that you can roll dice number 1, and there's 6 ways you can roll dice number 2, so 6 times 6 is 36. It's an application of the fundamental principle of counting. Okay, so we've seen it recently. So if we're taking a look at Pizza Planet, I was right, yeah, Pizza Planet. What's that from? Toy Story. That's right, it's from Toy Story. They offer 3 kinds of salads, 15 kinds of pizzas, and 4 desserts. How many different meals consisting of 1 salad, 1 pizza, and 1 dessert can we create? So this is more than 2 steps, but it's the same process that the definition described before, the theorem described before. We have our 4 different things we're creating to make our meal deal, right? You can imagine doing this at lots of restaurants do things like this, right? Where you have different options along the way. And so our first option, our first line is talking about the number of ways that we can get a salad. So how many salad options are there? 3. And then we have our pizza options. Wait, do we have just 3 options? I was getting 4. Sorry, I was thinking we were going to get a drink. It's 3 options, so sorry. How many different pizza options do we have? 15. And how many dessert options do we have? 4. So there's 3 times 15 times 4 different meal deals we could create. How many is that? It's quite a few. It's what? 180. It is 180, yeah. Better believe it. 180 different, we'll say meals at the end. Okay, 180 different meals that could be created. Now, not all of them differ by a lot, but I mean, 15 different pizza options in the middle is quite a few. There are going to be a lot of different, like legit different options here. Okay, so the next one we're going to take a look at is we're going to start looking at the definition or the words in our section's title. Our section is titled Permutations and Combinations. So this is our first encounter for the word permutations, okay? So a permutation of like objects. So let's write it down and then I'll describe what it really is. So n elements, and we're choosing R1 of which are alike, R2 of which are alike, and so on. Alike objects are indistinguishable. Then the number of ways this can happen is n factorial divided by R1 factorial times R2 factorial all the way down to Rn factorial. Okay, so there's lots of objects in your life that are indistinguishable kinds of objects. So jot some of these down so when you look back at this, you'll remember my examples because it'll help you sort of identify what category you're in. So our next example here is actually a really good example of such a thing, Starburst. And you could do this with kind of any kind of candy. So Skittles is a big one in my household. Go with Sour Patch Kids. Whatever object candy-wise you want to do, you get a package of them. There's usually multiples of one flavor, and multiples of another flavor, and multiples of another flavor. Everybody with me so far? So then it talks about things being indistinguishable. That's what it's talking about. So if I'm doing Starburst, one pink Starburst is completely indistinguishable from another pink Starburst. Make sense? Okay. So if you're trying to figure out how many different ways you could eat, say in this case the package of Starburst, if you eat pink flavor number 1 or pink little flavor number 2, it doesn't give you anything distinguishably different. Are you with me? So that's why you end up dividing by these factorials that identify how many of the repeated flavor options you have. Okay, so we'll do the Starburst example, but let me give you some other examples besides food that fit into this category, because there's quite a few. You can think about what happens when you're doing races and you're qualifying for something. So for example, my daughter will be doing a cross-country meet this weekend. And if they're trying to figure out who's going to be going on to another qualifying, like if it's a qualifying round for something else, whether it's cross-country or swimming or track, sometimes there's these preliminary rounds. Think about the Olympics, right? The top 3 people from a particular, heat go on. You know what I'm saying? It doesn't really matter if you're first, second, or third. If you're in that heat, you go on, right? It's indistinguishable whether you're first, second, or third in that particular category. If you were looking at in the Olympics, and you have different countries, and you're wanting to figure out the Americans versus the French versus the Ugandans or whatever like this, right? If you're not talking about the distinguishable people, you're only looking at the countries that are involved, then it doesn't matter if the American was getting or if the first place person was, a specific person. It only matters that they're American. They're in a category. So all the Americans would be indistinguishable from one another when you're thinking about it that way. There's an example that you're going to see in your homework where it talks about running flags up a flagpole. You've got a bunch of red flags and a bunch of blue flags and a bunch of green flags. Well, it doesn't matter which red flag's at the top. It just matters that there is a red flag at the top, right? There's an indistinguishableness to that. If you were talking about counting makes of cars, makes and models. So the make is the one where it says it's a Dodge or it's a Chevy or it's a Ford, right? And all you were doing was sitting on the counter and you wanted to count makes of cars that go by. It doesn't matter if it's a Ford F-150 or if it's a Ford Focus, it's still a Ford, right? They're indistinguishable. And even if you want to just be really specific, it doesn't matter if it's a Ford F-150 from the year 2007 or from the year 2009, we would put it in the same category too, right? So there's times when we want things to be indistinguishable, and you have to be careful on thinking about that. If you're doing something that's comparing men and women, right? Well, indistinguishable is the category of women, right? It doesn't matter which woman it is, it's indistinguishable. So you have to pay attention to how something's worded to decide if it's indistinguishable. Sometimes it's more obvious than others. So let's do our example with Starburst. So we have this package of Starburst. There's 4 red, 5 pink, 3 yellow, and 2 orange. If you were me, you'd just throw the orange and the yellow away. That's okay. Are you sad?
I like all of
them. You just give me the all pink packs. I'm actually good with that. I do that with Skittles too, by the way, and jelly beans. There's certain flavors that I like, and the rest of them I just don't care about at all. So we've got a bunch of Starburst here, and we're looking at indistinguishable ways to do this. It's actually funny. When I was in piano lessons when I was really little, my mom, when we would leave, we would get like a package of, they were Smarties, is what they were. And we would taste them along the way, and we'd guess which flavor it was. My mom and I would do this game all the time. I don't know why we did that. I don't know why we thought of it now. But it's like this too, right? Like they're indistinguishable, whether it's a purple Smartie from the beginning of the pack or the end of the pack. It's indistinguishable. So how many Starbursts are there? Count for me. Are there 14? 14. Okay, so that's going on top. So the total number of whatever objects you're considering is on top. And then the pieces on bottom are the pieces that make things indistinguishable. In this case, it's the colors individually. So red, I think, was listed first. How many reds were there? 4. So you do 4 factorial. And then you have the pinks. And there are 5 factorial. This is a good package of Starburst. What's next, yellow or orange? Yellow. How many yellows are there? 3. And how many oranges? 2. Okay. Now, let's talk about how we can simplify doing this, because we're going to get to some bigger numbers later, and you're not going to just want to multiply 14 factorial down to 1. That is not going to be a good course of action. The numbers get quite large very quickly. So there's got to be some easier ways to do some sort of cancellation with things we've learned about with fractions that will make it easier to work with. And there are. We're going to actually write the 14 factorial all the way out for this time, and then I'm going to show you an abbreviated notation so you can see how you can abbreviate it later. But I'd just like for you to write down 14, 13, just write it out. Not calculate it, but just write it down. And then you're going to do the same thing with the denominator with its individual pieces. So 4, 3, 2, 1, 5, 4, 3, 2, 1, 3, 2, 1, and 2, 1. It's a giant fraction. Everything on top is multiplied, everything on bottom is multiplied. What that means is you can cancel individual factors. Now, I want to choose the biggest one. The biggest one that I had in the denominator was 5 factorial. So there's this patch in the middle here that says 5, 4, 3, 2, 1. Do you see that? I could cancel out that 5, 4, 3, 2, 1 in sort of one fell swoop with the 5, 4, 3, 2, 1 up here. Okay, we'll come back to that red marking out in a minute to show you the shorthand. But let's continue. So is there other places where we can cancel things out? Well, sure there is. Somebody tell me one. 4 and 3 get you 12. Fantastic. So this 4 and 3 could cancel with my 12. What else? There's a 3 and a 2 that will get you a 6. So I do the same thing you're doing, Faith, where I usually look at pairs of things that cancel really nicely. Eventually you kind of run out of pairs, and they might not work very nicely anymore. So you might want to just look at canceling things individually. For example, you might be like, okay, well this 2, the 2 will cancel the 14, no problem, and I'll put a 7 here, right? Or maybe you would have done the 2 and the 2 together, and you would notice the 2 and the 2 go into the 8 here, so this 8 becomes a 4, but if the 2 and 2 had both been there, it would have become a 2. All right, so the cancellations are a little bit not unique a lot of the times, but they still give you the same answer. We want to cancel everything on bottom except the ones are irrelevant, so don't really worry about them, okay? And then once I've done that, one of the things to be really careful about is that you don't lose any of the pieces on top because it's often a mess. This is a mess, and this wasn't a big problem. So we need to make sure we capture all the pieces. So I have a 7 and a 13, 11, 10, 9, 4, and 7. Just grab a calculator, and I'd like for you to multiply out everything is circled in red. And then we'll talk about a shorthand way that we could have written this that's a little bit better than this. What'd you get, Lily?
720,720.
Okay, do you have confirmation on that? Mine's different, so that's why I'm asking for.
I think different. Oh, yeah.
Okay, what'd you get? 2 million. Okay, tell me what you have then. 2 million what? 520, yeah. So easy to lose one. That's what I'm warning you about. Be careful. There are over 2 million different ways you can eat that silly little pack of 14 Starburst. That's kind of crazy. I mean, isn't it? I mean, it's only 14 Starburst. Okay, so let me show you a shorthand way that you can do this that will save you a little bit of time when you're working. So I mentioned as we worked that I liked the biggest number on bottom. And so I'm going to write out my factorial until I get to 5 factorial, and I'm going to stop writing, and I'm going to leave it as 5 factorial. So I'm going to write out a bunch of them because the numbers don't get there very quickly. So 14, 13, 12, 11, 10, 9, 8, 7, 6, and 5 factorial. And on the bottom, I'm just going to move the 5 factorial to the front or to the back, just to kind of separate it from the rest. And then I'm going to write the rest of them out. 4, 3, 2, 1. 3, 2, 1, and 2, 1. So this 5 factorial can cancel with 5 factorial. Now, you can't reduce a factorial just by division. They only cancel out if they're perfectly identical, right? So like I can't stop at 10 factorial and say, hey, look, there's a 10 factorial and there's a 5 factorial, and I'll cancel it out and it'll be a 2 factorial. You can't do that. You have to be identical to do this. So the 5 factorial on the bottom cancels with the 5 factorial on the top. That's going to save us writing on this one a little bit, but it's going to save us some writing a lot on some others. And then we look for other pairs just like we would have before. And so we can do the same thing. Oh, look, 4, 3, and there's 12. And we can look at 3, 2, and there's 6. And then we can do, I'll show the same ones I did before. The 2 and the 8 gives me a 4. And this 2 and this 14 gives me a 7. And we go through and do the same pieces. Okay. So that's a shorthand notation that we're going to want later. Any questions on that? Okay, so this is permutation of like objects. The next one is permutation of unlike objects. So unlike objects have this notation that we're going to encounter, NPR, n factorial is on top, and n minus r factorial is on bottom. So what are unlike objects? Well, literally things that aren't alike. So if you had that Starburst package, but every color were different, those would be unlike objects. Okay? If you were doing the race and you were concerned about each individual, because they're each individually different people, those would be unlike objects. Right? People are not the same as other people, right? If we're not categorizing them in any way. So anything that you can distinguish between the objects, and that's the purpose, right? I want to count the cars, and I want to write down exactly which cars went by. Not the make, not the color, not the year. I want the exact vehicle, right? And they're probably not going by twice. That would be our assumption. Okay, so unlike objects. So you see on top n factorial, and you see the n listed in front of the p. The n represents how many people or how many objects you're choosing from. So imagine you had some kind of candy where there's so many colors, just crazy numbers of colors of candy, okay? So let's say there's 15 colors of candy. Well, there's 15 total pieces of candy, and they're all different. Well, the 15 would go at the front. There's 15 pieces of candy, and they're distinguishably different, and you're only going to eat 5 of them. Well, the 5 would go at the back. Right? The 5 is how many you're choosing. So we have our class with me, that's 13. There's 13 individuals in the class who at the beginning, and then we wanted a committee of 3 people to go and buy donuts, right? Well, that's the 3 at the end. We're choosing 3 of them to send. Okay, are you with me? Okay. So I shouldn't have said committee, but we're a group of 3. We'll talk about committees actually in a little bit. But that's the idea here, okay? So the number at the end is how many we're choosing. Notice the denominator. The denominator is not the number we're choosing. In fact, it's the number we don't choose. So think about this if you were to do like a race, and you wanted to award the top 5 people who finished medals. They're medals 1 through 5. There's 30 people running the race. Well, there's 30 at the beginning. There's 5 people who win medals. There's 5 at the end. But that means there's 25 people that don't get anything, and it doesn't matter what order they come in, they still get nothing. That's why you're dividing by the 25. Because the 25 losers in this case would be indistinguishable for the purposes of the problem. Does that make sense? So the reason we're dividing by things in both of these cases is because they become indistinguishable. We can't tell one apart from the other, right? If the top 5 people all mix up their places, they get different medals. But if anybody in the bottom 25 runs and does differently, it doesn't affect the outcome, not in terms of the medals, okay? So here's our example. We have 30 contestants, and they're all putting their name in the hat for a raffle. First place wins $100, second place wins $50, and third place wins $25. And how many different ways can the prizes be awarded? So the question is it distinguishable the way in which somebody wins a prize? And the answer is yes, because the prizes are different. If I win the first place prize, I win something different than I win the second place prize, right? That's what makes this indistinguishable, is because the prizes are different. Much like my example with medals. First place medal is different than the second place medal. They're distinguishable. But there's still 27 people here who don't win anything, right? Those are the indistinguishable pieces of this particular problem. So what goes on the top is the number of people that are in this particular game or raffle. That's my 30, and it's a factorial. And what goes on bottom is the number of people who don't win things. So you can actually look at this and calculate it. If you want to write it down and you go, oh, well, there's 30 minus 3, that's fine too. If you want to jump to the fact that it's just 27, that's okay as well. Either way, so you skip over that first step if you wish. And then we're going to figure this out, and we don't have to write out 30 to 1. Are you with me? That's that notation I was talking about and where it's going to be helpful. I do not want to write out 30 down to 1. And if the number gets bigger than 30, I really don't want to write it out. So I write out the 30 to 27. So 30, 29, 28, and 27 factorial. And then the bottom, I don't even have to write it out. It is identical to the 27 factorial, which is why I stopped where I did. And those cancel. This is much cleaner than the last problem. I just have 30 times 29 times 28. And what do we get? Say it louder for me.
24,360.
Oh, your voice is gone. I'm sorry. 24,360. There's 24,360 ways this can happen. Now, in this particular scenario, with this particular problem, there is another way to do this problem. That happens occasionally. You could do this problem as a fundamental principle of counting problem. So let's talk about what it would look like if you did that. If we did this as the fundamental, that was not the word letter I wanted an F, fundamental principle of counting, get my letters in the right order. We could say, well, I've got 3 winners, right? And because they're distinguishably different, I could use fundamental principle of counting. How many people are going to win? I didn't say it right. We know it's 1. How many people could win first prize? 30. It could be any of the 30 that win, right? Especially if it's a luck game and not a skills-based game like my cross-country running example, right? But whoever wins first place does not get to still be in the running for second place. So how many people could win second place? 29. And how many could win at that point third place? 28. And do you see the same 30, 29, 28 as we got in our other version of this? Yeah. So this is another way of doing this particular problem when we think of it from a different perspective. Okay, we're going to do one more today, one more type of accounting principle, and we'll push pause.
Wait, so.
Oh, yep.
Sorry.
You're fine.
On this, the example for like the first portion you did.
Yep.
That can only be used like on big numbers, or could you?
Oh, no, it can be used on small numbers. Yeah, it absolutely can. Yeah, it's not a big, small thing. It becomes more helpful to do the cancellation the bigger the numbers are to cancel things out.
But you could just do it on any problem.
Sure.
Cool.
Yep. Okay, the last one for today is combinations. So when we're doing something in a combination, the order doesn't matter. It is distinct. I didn't write that right. Let me say it again. The winners are indistinguishably different. Okay? So in this case, this would be like what happens when your runners cross the finish line and you just take the top 3 and you move them on to the next round, right? Like our Olympics example. It doesn't matter if you can have first and second place or third place. You're all the same. They are all indistinguishable, the winners are. So in this one, what you see happen is you see the total number of people that ran or participated in the game on top, just like the last one. You see the losers, the n minus r, the people who don't win something. And you actually see a factorial for the number of winners as well. Okay, so the number of losers get a factorial, the number of winners get a factorial. It is indistinguishably different if you win from anybody else that wins, and is indistinguishably different if you lose from anybody else that loses. Now, obviously, there's a difference between winning and losing, but you've just put people into these two categories, is what's happened. Winners in one, losers in one, we count them total, we divide. So when you look at this problem, 30 contestants name in a raffle, much like the last problem. But the difference is 3 people win, but they win the same thing. So it doesn't matter if your name is drawn out first, second, or third, you all win. Those are indistinguishable from one another. And it's also indistinguishable if you lose. So we still have our 30 factorial on top. But the bottom is the number of people who win. Well, that's 3 factorial. And the number of people who lose, that's 27 factorial. Because it doesn't matter if you're first, second, or third. It's indistinguishable. Or the order doesn't matter. That's how it's phrased on the previous slide. So we can write out again 30, 29, 28, and 27 factorial. And I can have my 27 factorial at the bottom. And then I need to write out the 3, 2, 1. So 27 factorials cancel. The 3 and the 2 are much smaller than what's on top. So you can cancel them out piecewise if you wish, or you could do it like join together and realize, oh, 3 times 2 is 6, and cancel that out together. That's fine too. So if you just did it piecewise, you might say, oh, look, 3 and 30, that's 10. You could either then do 2 and 10, or you could do 2 and 28, that's 14. Whatever ones you see, it doesn't matter. In the end, you end up multiplying what's remaining, which the case that I've got a 10, a 29, and a 14. And what happens? What do you get on that? What was it? I have something different. 4,060 is what I have as well. Can you check yours?
Yep.
Okay, is that all right? So 4,060 ways that this can happen. That's a lot smaller than the last one, right? That makes sense. We divided by something extra. We divided by 6. 3 times 2 is 6. So of course it's going to be smaller. That makes sense. It should be smaller. So what we're going to do when we come back next time is we're going to take different examples and we're going to try our best at figuring out which category is it in, or categories. How could I do this problem? What are the red flags that tell me this is the type of problem this is? And then how do I go about actually solving it after that? Okay? So we'll stop here for today.